Hello, everyone. Good morning. My name is Michael Xing. I'm a principal software engineer from Microsoft. And I worked in Windows team previously about 10 years. And then I moved to Azure CSI team. So in Windows team, I was the dev owner for Store NVMe and Store HCI, which are Windows drivers on NVMe and AT devices. Also represented Microsoft in NVMe community and the SATA community. After moved to Azure CSI team, which called Cloud Server Infrastructure, I worked on specific drivers and firmware on the hardware in data center. So today, I will talk with Danyu about a new Windows monolithic NVMe SSD driver for cloud environment. So Danyu is a principal engineer development lead in Windows performance team. And we also have Liang from Azure performance team worked with us on this project, but Liang cannot make it into today's meeting. So Danyu and I will talk through this presentation. So first, I want to make clear that the performance results presented in this talk are based on a prototype driver in a controlled lab environment. Also, this driver is not intended to replace the current Windows storage stack, and it's not in production yet. So this is our agenda for today's talk. First, we want to talk through the motivations. As people already know, Windows has been in market for years, and the storage stack has been stabilized for a long time. So why we need a new driver here? So that's mainly because the storage device advances, and also because the existing Windows driver stack becomes a little bit heavier on the fast device in the cloud environment. After that, we'll talk about the new Cloud SSD driver design. And then I will transit to Danyu to talk about the performance evaluation and the performance results. So why a new driver here? So within these years, we see the popularity of the I/O-intensive workloads, which are high throughput, low latency workloads in cloud, leveraging local attached storage. It's also because in these years, the storage hardware and advances in both areas, in the interfaces and also in the media. In the interfaces, it goes from SAS, SATA to NVMe, and in the media side, it goes from the rotational media to non-volatile memory, and for example, the 3D cross-point. So this exposes the existing Windows storage stack get heavier compared to the faster storage hardware underneath. That makes us think there is innovation needed for a new storage software stack, targeting on the cloud environment and still preserving maximum user application compatibility. We also use this project to explore the ideas to improve the Windows storage stack for next update. For storage technology side, so the data center SSD storage in these years has been moved into NVMe SSDs. So we see the trend from the SAS SATA interface advances to PCIe NVMe. And for the media side, as I talked previously, we see more and more SSD using NAND or even faster technologies like 3D cross-point. So below is a table talking about the protocol bandwidth and IOPS can be delivered by these technologies. If we focus on the third row, the Gen 3, we can see the SATA for the single device. It can deliver about 100K IOPS. The SAS device can deliver 250K, while the PCIe Gen 3 4-lane NVMe device can deliver 1 million IOPS. With 16 lanes, it will be able to deliver 3 million IOPS. So that's the storage hardware side advances. The NVMe comes here, play a big role, because NVMe has been designed from beginning to capitalize on high IOPS, low latency, and the internal parallelism of the SSDs. Also, the IOQ's design in NVMe gives a very good opportunity for it to scale the I/O initiation and completion on a balanced processor usage. So the diagram shows an example which one I/O pair, one submission queue and a completion queue assigned to each logical processor. So this processor can be used in a balanced way. Another side is that NVMe minimizes the hardware register access in the I/O path. So basically, it only needs one hardware register access when sending down I/O and one access in completion I/O. We know that the hardware access is a very expensive operation in the I/O operation. So compared to other protocols, which may need 6 or more hardware access, NVMe uses much less here. So besides of the storage hardware advances, the users use pattern for the storage I/O virtualization in cloud environments. It also improves. We know that in the very old days, the storage access mode is the emulation access, which is the Hyper-V emulates hardware in its layer and then gives the actual real command to the real hardware. That's a slowest method. Then the things got improved. There is a synthetic method got introduced in Windows. That's a faster way, but it also still have some overhead. I have a table below shows the overhead in different layers. So the table from the top, we can see in the VM area, we have the Hyper-V VM enablement, which is the Hyper-V part running in VM. It takes about 5%, and the OS storage stack takes about 15%. Underneath it's a VM host like component, it takes about 20%. And on host side, the Hyper-V host component is also 20%, while the file system and OS storage stack each takes about 10%. The third portion is the hypervisor itself. It takes 15%, mainly related to the interrupt delivery. So actually this area got improved a lot by the new technologies such as a post-it interrupt. So with the parallel virtualization get into here, with this overhead, it seems still not enough for the fast device in the cloud environment. So the VM access mode got improved again into the DDA, which is the Hyper-V discrete device assignment. This mode allows to pass through a PCIe device into the VM directly. So the VM can access a device directly exposed by the host. So this mode applied to the NVMe device, it has some security concerns especially. because it will allow the VM user to access admin queue, which can send down whatever admin command it wants. So there is an improvement again based on the DDA mode called NVMe Direct. NVMe Direct is a method to be able to assign an NVMe device directly from host into VM, let the VM access the I/O queues directly, just like it shows in the diagram below. On the right side, these are I/O queues being exposed to the VM. So the VM side has this NVMe device which use the I/O queue directly. On another side, the admin queue got intercepted by Hyper-V, so that if there is an admin command sending down, the Hyper-V will intercept that and to check it to see if the command need to be monitored or the command need to be blocked. So the device exposed into VM side has a virtual admin queue, which is not directly using the actual physical admin queue. So with the storage hardware advances and the VM I/O mode changes, the major left overhead is the OS storage stack. So let's review the Windows storage stack so to see what it currently can support, what's the benefit from there, and what's the limitation from that. So this is the existing Windows storage stack layer. So I think most of you are familiar with that. So let's talk from bottom up about the driver stack. Then we talk about the I/O coming down from top. So from bottom, it's a storage controller, that's a hardware. On top of that is storage port driver, which consists of kernel mode, shared DIR, it's store port, and a Miniport driver. In here, an example is store NVMe. And on top of the storage port driver, there might be a lower disk filter driver. And then on top of that is storage class driver, also consists of two parts. One part is the shared kernel library, it's a class PNP, and another part is the driver itself. In here, example is disk.sys. On top of the class driver, there can be upper disk filter driver. Then another filter driver is partition manager, manages the storage device for all the partitioning work. So with this stack there, when the I/O or request come down, it's in a IOPS like data structure, passed down from the, so example is that a user trying to access a storage device. Typically, he will open a handle to a file and then sending down request. So this request goes through the file system layer, which is not listed here. So there is another stack work closely with the storage stack. It's a file system stack, including the volume manager. So with the IOPS coming down from the file system stack, it reaches partition manager, and then goes through the upper filter driver, go to the class driver. In here, class PNP translate into a SCSI command and send it down. And at the port driver and Miniport driver layer, the command being translated to the actual protocol command. In here, example is the NVMe command, and then the command will be sent to the hardware. So besides of the drivers like written by Microsoft, the Windows stack has like filter drivers, which can be developed by like anyone, developers or vendors, to add features or modify some behavior without a full driver development. So this diagram basically shows an example about an NVMe device, exposes 2 namespaces. Each namespace is represented as a disk. So from the bottom, you can see the PCI bus PDO, then there is the adapter FDO, then bus driver, filter driver, FDO, then go to the disk stack, have the PDO, filter, FDO, upper filter, FDO, etc. So the filter driver allows people to develop some specific feature or specific functionality without a full driver rewrite. So besides of changing the existing driver behavior, when people want to support the new hardware with new interface, so they will need to write an actual Miniport driver. So this is a port driver library and Miniport driver model, which the port driver exposes the controller interface and the unit interface is corresponding to the disk interface. So it talks to the Miniport driver. And then these two works together to process the initialization, I/O, PNP, power, and all other requests. And then it sends the protocol command to the actual hardware. So the general division here is that the port library controls all the common logic, and the Miniport driver works with the actual protocol. So with all these diagrams, let's summarize what's the Windows storage stack. So it's designed to be a layers of driver, with each layer has a specific responsibility. So in previous slides, we saw the bus driver, device driver, and the filter drivers. And the Windows storage stack is also a SCSI protocol-based stack with a translation to other protocols at the end or at the bottom of the stack. In history, there were multiple port driver, Miniport driver models there, like SCSI port, AT port, then got consolidated into store port model. So some advantages of the Windows storage stack. So it's a single storage driver model, supports diverse hardware for different markets, including the client and enterprise markets. Also, it supports different interfaces like ATA, SCSI, NVMe, etc. And this model reduces storage driver development complexity by providing the class driver and port driver libraries, the two shared libraries we showed in previous stack. And this layered model also provides flexibility of the filter driver development to be able to do small tweaks in the stack. With the cloud environment emerges in these years, and in that cloud environment, the hardware is limited choices of hardware and owned by the cloud provider. So this gives us an opportunity to look for a new driver model with a reduced software overhead. So with that, we are looking into the Cloud SSD driver stack, which is a new driver we have been working on. So in the design principles, what we want to focus on for the new driver. First, we want to focus on the cloud environment for specific customer scenarios, which is the IO-intensive, CPU-sensitive workload. It's not intended to replace the existing Windows storage stack, and the work is targeting NVMe device only. We want to have a more efficient I/O path so that we can reduce the I/O path length and the CPU usage. So we reduce the driver stack depth by merging multiple storage drivers into a monolithic driver. And also the I/O translation is from the IOPS to NVMe and sending to the device directly. So this, in the middle, there is no any other translation. And also, the new driver improves the queuing latency by reducing the IOQ layers. In existing Windows storage stack, there are multiple layers of drivers can have queues, which can impact on the I/O latency. Another area we looked in is the IOPS path, which now the new driver supports asynchronous IOPS path. This allows the vendor-specific read-write command to be sent down using this path as a fast I/O path. So traditionally, the IOPS path is considered as slow path because a lot of work there are synchronized. You cannot send down multiple requests at the same time from the same thread. This driver, we also make it a modular design. It's similar as the Miniport driver model, which the core library contains the general storage device logic, and the driver itself talks to protocol-based functionality. And the new driver supports both interrupt I/O mode and also the polling I/O mode. So this is the Cloud SSD driver stack. It has a comparison with the existing store NVMe stack at the left. The new stack is on the right side. So from this diagram, you can see the major difference in the driver stack is that the new driver on the right side of the Cloud SSD driver replaces the previous storage class driver and storage port driver stacks. So basically, there are multiple drivers got compressed into the same layer. Let's take a look closer into the I/O path comparison between the existing storage stack and the new Cloud SSD driver stack. So on the left side, with the current store NVMe, you can see when the I/O or IOPS sending down from the file system layer, it goes through the class PNP and get translated into SCSI command here, and then sent to store port, which store port, it go check for a long queue to see if the I/O need to be put into the long queue or not. Then the I/O goes through the adapter queue before it's sent to the Miniport driver. So after store NVMe, the Miniport driver gets the I/O, it translates the SCSI command into the NVMe command, then send it to the NVMe device into the corresponding queues. And on the completion path, you can also see that when a device signal I/O need to be completed, the Miniport driver uses the interrupt handler or DPC to pick up the I/O to be completed and completed back to store port. Store port schedule another DPC to complete back to the class driver layer and then complete back to its higher layer. On the right side, when I/O getting sent down from the file system stack, it goes into CSSD driver directly and go through the adapter queue, then translate into NVMe command directly, sending down to NVMe device. On the completion path, it's also with signal from the device, says, okay, this I/O is ready to be complete. Then it uses the interrupt handler or DPC to complete it. So compared to the left side and the right side, the I/O path got a significant reduction. Yeah, thanks. So with this I/O path improvement, we do have some limitations in existing Cloud SSD driver. The first one is that the new driver is designed for controlled environment only. such as for Azure Cloud. The features this driver support is not on par with the general purpose driver. Also, it's targeted to NVMe SSD only, doesn't support other storage bus interfaces. And because we compress multiple storage drivers into the same layer, the Cloud SSD driver does not support the low disk filter driver, especially when the driver intercepts SCSI command, because there is no driver sitting above the filter driver translate into SCSI. So with this, I will translate the talk to Danyu to talk about the performance evaluation and the performance results.
Thanks, Michael, for the great introduction, for the motivations of this new driver, for the advance of storage stack, and also the design principles of the CSSD driver. Now I'm going to talk about the performance evaluations, as Michael just mentioned. The performance improvements as well as the reduced overhead is one of the key design principles for this new driver. So this driver is most designed for the cloud environment. So for the performance test here, we only test the drivers in the VM, in the virtualized environment. This slide shows the test configurations. For the physical machine, we're using an Azure Gen 6 machine. It's a 2-socket, 26 logical processors, and it is using Intel Skylake processors. For the storage side, we are using Intel PCIe Gen 3 by 8 half-height, half-length P4608 NVMe SSD. This device is capable of delivering 1.6 million IOPS per device. Now, in the VM side, we are using a 24 VM VP. So the reason we are not using the full-size VM is that you can see later in the results. With this size of VM, we are already able to saturate the device. For the storage, we are using NVMe Direct. As Michael mentioned, this is the fastest interfaces to attach to VM. For the OS, we're using the latest OS for both the host and guest. The testing and experimental settings. The test tool used here is the disk speed 2.018a. So this is the open source test load generator, and is very popular used within Microsoft and external vendors when we're testing the I/O throughput for Windows environment. The source is available in the GitHub, so there's a link. You can look at how the driver, how this load generator is constructed. For the experimental settings, we use the NVMe device as a raw disk. So because here we are most interested in the lower half of a Windows storage stack, so we bypass the file system and using raw disk to test our performance. And with 1 disk speed instance per disk, and we vary the number of I/O threads to see how that performs when we scale the worker threads across the system. And we're using 128 queue depths per thread. Now with enough worker threads, we were able to saturate the whole device. For the testing, we're using 4K random rate, 4K aligned, and non-buffered I/O. So these are very standard settings when we're testing the high IOPS throughput. We look at 3 different metrics. The first one is throughput, how many IOPS you can achieve per second. And the second one I look at is path length. So how many cycles, CPU cycles you needed to complete each I/O. The last one we look at is latency. So here we're most interested in the synchronized I/Os. For the single thread, single queue depth, we look at how many milliseconds we need to complete I/O. So for these tests, we're not looking into the bandwidth because the key metric here is to reduce the overhead when you have a very high IOPS. So we're not looking into bandwidth here. So the first the comparison is throughput IOPS. So this graph shows the comparison between the store NVMe and the CSSD. Store NVMe is using Microsoft current storage stack. So using the class driver, port driver, and the Miniport driver is store NVMe driver, which is Microsoft-owned NVMe driver. CSSD driver is our new storage design. You can see that for the low IOPS, low worker thread, all the way from 1 thread all the way to 10, 12 threads, the CSSD driver is perform much better than the current store NVMe driver. The reason for that is that we are CPU bound on all the worker thread. So because CSSD driver has much less overhead, it delivers much higher IOPS. In some cases, it can provide up to 40% I/O throughput. And also, you can see that the CSSD driver can fully utilize the throughput with only 10 I/O worker threads, while the NVMe driver needs 14 I/O worker threads to deliver that same throughput. So it's very important for a lot of the workloads because the CPU is very crucial resources. And the more CPU you use for deliver those I/Os, the less CPU used for the user mode application to do actual work. The next one we'll look at is latencies. Here we look at two different scenarios. One is single thread, single queue depth, synchronous I/Os. And you can see that we also compare NVMe and the CSSD. The most interesting part is the third data column, the average latency. You can see that with less queuing in the middle of CSSD drivers, this driver can provide up to 5% improvements on the synchronous I/O. And also because of all these improvements, the throughput also improved by about 11%. The second one we look at is 16 thread, 128 queue depth. With these configurations, both drivers already push their limit to the device limit, 1.6 million IOPS. But the CS driver provides much better performance on the path length. And the most interesting part is look at the 3-9 latencies, the tail latencies. Because of the queuing reductions in the middle, it provides up to 25% reduction on the queuing on the tail latency. The last one we look at is pathlength comparisons. And the path length here is measured by CPU cycles per I/O. And x-axis is the number of worker threads, y is k cycles, CPU cycles for every I/O, including the I/O initiating and I/O completing. Now you can see that across the board, from 1 to 16 worker threads, the CSSD driver provides up to 30% path length reductions. So, to conclude, the rapid storage hardware advancements is really can take advantage of these high efficient I/O paths. We have talked to different workload services and workload developments. They really think that to achieve 1 to 2 million IOPS, 3 million IOPS, the CPU overhead to kind of achieve these IOPS is way too high currently. And they really want a more efficient I/O path so that they can leave more CPU cycles for the real user mode applications. Now, existing Windows storage stack also has a lot of advantage and is provide flexibilities for the developers, but has some opportunities to further optimize for the controlled cloud environment. Now, Michael, me, and Liang also try to explore the ideas, and we develop these proto drivers to see what is the future Windows storage stack innovations. We want to demonstrate the performance benefits, and the key part here is that we also want to preserve maximum user application capabilities, because there's also some ideas existing currently using, for example, using the user mode storage drivers, but the main drawback of those approaches is that you have to rewrite all the user mode applications, and also a lot of existing filter drivers, models won't work there. So we believe with a cloud-specific driver, we can enable the fast development of the high-performance VM skills in the cloud. So any questions?
So your numbers are from with interrupts, or did you do folding as well?
So the number is with interrupt.
Interrupt.
Yes, that's right.
So you would expect better numbers with folding?
Yeah, we do expect a slightly better number with pooling, but the pooling is also the CPU overhead. You probably can achieve a slightly better IOPS, but the CPU overhead will be worse than the interrupt mode. Yeah.
And also because this is Azure only, is this going to be supported by Azure Stack?
So,
There is no current plan to put in Azure Stack yet.
Okay.
Is there any impact at all on write amplification in the SSD from what you've done?
I don't think so. So basically, with this model, the I/O pattern is not changed, and with Then it goes through the similar like software layers, just shorter software layers. But the pattern doesn't change, so the red application won't change by this regard.
Okay, thank you.
Were any of these performance numbers taken through the asynchronous IO path, or was it all just direct submission?
That path, we don't have a number here to disclose, sorry.
And then the second question, if I may, with the direct map submission queues, how are you handling coordination of the doorbell register?
Sorry, can you please repeat this one?
So you're mapping individual submission queues up into the user space with virtual machines, but there's a common doorbell register for those submission queues. How are you coordinating access?
I think you are talking about the NVMe direct part.
Yes.
So in that part, the IO queues is not directly mapping into the user space. It's actually the IO queues mapped directly into a VM device. It's still an NVMe device. There will be driver loaded in the VM space to manage it.
Yeah, with NVMe Direct, you will see NVMe driver and devices directly showing up in OS. So it's not directly to the user mode. So all the user applications and user mode in the VM won't change.
So the idea is basically that the NVMe device on host, there won't be storage driver loaded. The IO queues will be directly accessed from the VM side, from the VM device.
So,
Do you have any performance number for 3D cross-point SSD like Octane SSD by polling driver?
Yeah, we do testing it, but the results we don't expose that yet.
yeah, so I can tell you the performance is even better than this one.
Yeah, basically the summary we have with that is that faster the storage device is, the better performance number and the better latency number will be shown up with the new graph.
Have you looked at the different performance of SRIOV hardware support in the devices?
So for SRIOV support, it's not currently in Windows for NVMe device, so we have not compared that part.
On your latency tables, was that showing that the 3.9 in a single threaded case, was that showing that the 3.9's latencies were lower than the average latency, or I'm curious why that would be?
Let me see which one.
So that in the
That's a good question. So I will go back double check. Yeah. Maybe I can reverse the table. Yeah, it's a good question. Yes. Yeah, most likely I think the 3.9 numbers is average latency and the average latency is the 3.9. Yes. Thank you. So any more questions? Okay. Yeah. Thank you.
Thank you very much.
Thank you.